welcome back to this video on sampling distribution models. From any one random sample, the best guess of the true proportion is the observed sample proportion. As we know, each random sample is going to be different. And that's due to natural variation, sampling variation. Our challenge is to use the sample to not only guess the true proportion, because that's what we're interested in the entire population, which we know is difficult, if not impractical, to find information about without taking good random samples, but also to guess how good that guess is. Quantifying the uncertainty in our guesses is the core of statistical thinking. It's unusual to have an entire population to work with, as I just said. So usually we draw a sample at random. That distribution of proportions from all possible samples is known as the sampling distribution of the proportion. If the conditions are right, we can use a normal model for sample proportions, and we can know just what the mean and standard deviation of the normal model should be. To use a normal model, we need to specify two parameters: its mean and standard deviation. The center of the sampling distribution of a proportion is naturally at P, the true proportion, which we'll use for the mean of the normal model. Sample proportions are very special. There's a mathematical fact that lets us find the standard deviation of their sampling distribution without a simulation. It gives us an exact answer if we know the true proportion. So if we write P for the true proportion, and Q, we'll let that represent 1 minus P, and N is always going to be the sample size, then the standard deviation of P hat, which is our sample proportion, is the square root of P times Q, and again, Q is just 1 minus P over N. This is the standard deviation of the proportions of all possible samples of N values from the population. It's not the standard deviation of the data. The figure illustrates the sampling distribution model of a proportion is normal with a mean of P and a standard deviation of the square root of P times Q over N. Because we have a normal model, we can of course use the empirical rule 68, 95, 99.7, or we can look up exact probabilities using the table or technology. For example, 95% of normally distributed values are roughly within 2 standard deviations of the mean. So about 95% of samples will have the sample proportions within 2 standard deviations of the true mean, or the true population. Knowing that, we should not be surprised if various polls that may appear to ask the same questions report a variety of results, right? Again, because of natural sampling variation. But we would be surprised if there was too much variety, because we now know how much variation to expect from sample to sample. Such sample to sample variation is sometimes called sampling error or sampling variability. And we kind of talked about this in chapters 11 and 12. So what I like to do in class is I like to do a Reese's Pieces activity to show you what we're actually talking about. So if you have the funds, what I would suggest is that you purchase a pack of Reese's Pieces and take as many samples of 20 Reese's Pieces as you can and count the number of orange. And then you're just going to follow these steps here and answer the questions. I also would suggest that you go to this applet, which is a simulator, which is going to simulate this p-hat sampling distribution idea, so that you get an idea of what we're talking about here. If I could sum it up, essentially what you're going to do is try to guess what the true proportion of orange orange Reese's Pieces are. So the company claims that it should be about 50% of every bag is orange. But we know that not every sample is going to be like that. But we also know that when we're dealing with real life populations, we also don't know the true proportion, P. So we take random samples, and out of those random samples, we get p-hat, which is our sample proportion. And when we take all of our p-hats and pile them up, they should pile up around the true proportion. So in other words, if you were to take samples of 20 Reese's Pieces randomly and count the number of orange Reese's Pieces that you find, and then divide that by the total number. Let's say you take a handful of 20 Reese's Pieces and 5 of them are orange. You would just, to find p-hat, you would do 5 divided by 20. Let's say you took another random sample of 20 and 16 of them were orange. You would find p-hat by doing 16 divided by 20. If you take many samples over and over and over from the same population, you're going to end up with all of your sample proportions, p-hats, centered around the true mean, p. So in the case of orange Reese's Pieces, it should center around 0.5 or 50%, because that's what the company claims is the true proportion of orange Reese's Pieces. So again, I would suggest that you do that little activity and answer the question so you can kind of see what's going on there. And then you'll want to go to this website to also try this simulator so you can see what a p-hat sampling distribution is. And then there's questions for you to answer there as well. And one of the main points that you want to get from this little activity is that as the sample size increases, you're going to notice the spread, and in this case, that could be the standard deviation, is going to decrease. Something else that's important is that, let's say you took a random sample of 80 Reese's Pieces, right? The sample size, as long as it's large enough, should get you close to the true proportion. So that means we would expect the proportion of orange pieces to be about 50% or 0.50 plus or minus about 2 standard errors. So our conclusion is, although the sample proportion varies from sample to sample, they seem to pile up around the population proportion, which remember is P. So again, you're going to have all these p-hats, all these sample proportions, and they're going to pile up, and around the center is going to be P. And that's the end of this video. We'll pick up with the conditions that we need to check to use a normal model, and we will solve some problems.